outside of this workshop also, I suppose. So we are going to understand how difficult or easy it is to win a game, for whatever easy means, whatever difficult means, whatever computation means. So you may have got some overview of all these things. So there are many games we play, right? Chess, Sudoku, Ludo, Snake and Ladder, all of those. And there are also some games that you learnt about in this workshop. So we are going to see what it means for a computer to probably solve these problems. Right? An online chess that always wins against you. Why does it find an algorithm that wins against you most of the time? Okay, so we will start with some problems and then we will see how to solve them. Most of the problems you have seen in this workshop. Some of the problems you may have seen outside of this workshop. Okay. So let us begin with one problem, which is an easy problem, which is primes. So I am going to give you an integer n, which is greater than or equal to 2. So given n, I want you to decide if n is prime or composite. Or composite. It is a simple problem you have seen. So I am not including n equal to 1. So if I give you 3, 5, 7, 11, you have to say prime, otherwise you will have to say composite. So we know algorithms to do this. So we will see some problems and then we will see some algorithms to solve these problems. Okay. So next problem is odd cycle detection. So you are given a graph, I suppose you know what a graph is. It is a set of vertices together with a set of edges. So given a graph G, so V is the set of vertices and E is the set of edges, right. So for example, let us say this is the graph. So this has 5 vertices and the edges are 1, 2, 1, 3, 3, 4, 2, 2, 4, 2, 5, 4, 5. Okay. So a bunch of vertices and a bunch of edges. Decide if G has an odd cycle. I do not know if I need some spacing. It's an odd cycle. So what do I mean by an odd cycle? A cycle whose length is odd. Okay. A cycle of length, say 2k plus 1. Right. So this graph does it have an odd cycle? It does, right. So the cycle is 2, 4, 5. For instance, this graph does not have an odd cycle. So similarly, 3 is prime, 4 is composite. Okay. So this is a yes instance of the problem and this is a no instance of the problem. So maybe I should note it. So this is a yes instance, it's a no instance. Okay. So the next one is something you may have seen, Boolean satisfiability. So have you heard of this problem? Okay, so maybe you should say then what are you given and what should you do?
Given some clauses, we have some, I don't know, what are those called inside the clauses? Variables. So given clauses and variables, we have to see that if it satisfies truth or false.
The variable can take value from 0.
Okay, so that's the Boolean part, right? Okay, so what is the input? You are given a formula. So let me call this formula phi, it's on some n variables, okay. So an example would be something like x1, x2. Okay, it's a formula on 2 variables. It's connected by a logical connective, and or not. These are logical connectives. Okay. So it's called a propositional formula because we are going to use logical connectives. It's phi. Okay. Decide if there exists a Boolean assignment. So I want to decide if there exists a1 to an, where each of these are Boolean, such that if I substitute a1 to an in the place of x1 to xn, the formula evaluates to true. Right. So what is an assignment? So this here is called an assignment, a Boolean assignment. because it's taking values in 0, 1. Right? And you call this satisfying because if you substitute a1 to n in the place of x1 to xn, you are getting 1. Right? So, for this formula, can you find a satisfying assignment? 1, 1, right? So, a1 equal to 1, a2 equal to 1 is a satisfying assignment. So, what about, say we will call this v1. So, this is x1 and not of x1.
No.
There is no such satisfying assignment, right? So, if I substitute 1 or 0, it will like always evaluate false. So, this is a yes instance, this is a no instance. Right? Okay. The next one is the flipped version of this, which is Boolean unsat. Right? So, I am given a formula phi. I want to decide if phi is unsatisfiable. Right. So, unsatisfiable means that no matter what you plug in for all a1 to an in 0, 1 to the n is always false. So, for instance, for unsat x1 and, so this formula phi 2 where x1 and not of x1 would be a yes instance. Yes, it is unsatisfiable, right? Is that okay? Okay. So, these are some problems, some more problems. So, here there are, okay, so maybe I should make it, so let me change this to x1 or x2. Right. So, 1, 1, 1, 0, everything except 0, 0 is actually a satisfying assignment, right. So, there are many satisfying assignments. Now, I want you to search for a satisfying assignment. Okay, so, given phi in x1 to xn, find an a. So, I am just using some shorthand because it is difficult to write a1 to an such that is that okay? So, there is some issue with that. So, what if I give x1 and not of x1? Yeah, so it may not exist. So, you have to find one if one exists. I mean, one may not exist, right? If it exists, find it. So, now here there are many satisfying assignments, right? Anything except 0, 0, essentially 3 satisfying assignments. So, now I can ask you to count the number of satisfying assignments. Given phi, count the number of is that okay? So, so you must have heard of this concept in the workshop. So, can you tell me what you are given, what is a pure Nash equilibrium?
Given a set of players and a set of strategies, is there a Nash equilibrium?
So, who is answering? Okay, sorry. Yeah. So, given a set of players
And their respective strategies,
okay,
is there a Nash equilibrium for?
is there a Nash? So, what is a Nash equilibrium?
A strategy wherein if I unilaterally deviate from it, it won't increase my utility.
Okay. So, exactly what you are saying, I am going to write. So, maybe I will say given a game. So, when I say given a game, how was the game described?
Players and the set.
So, it was like a table, I think, like in rock, paper, scissors, right? So, the matrix, every cell had 2 entries in a 2-player game. Okay? So, given a game, let us say with n players, it depends on the game. I think in Prisoner's Dilemma there were 2 players, in rock, paper, scissors there were 2 players and so on. Right? N players and m actions. decide if there exists a pure Nash equilibrium. So let's call this game G. I should give it a name. Okay, decide if there exists a pure Nash equilibrium in G. So a pure Nash equilibrium is a strategy profile. I mean, it's exactly what you said, right? So a strategy for all the n players such that for every player in 1 to n, so there are n players, right? So if he selects SI star as the strategy and the rest of them use, I don't know, I think this was the notation, right? I don't know if it was superscript or subscript, but right, this is at least as good as choosing anything else, where SI is all the possible actions he can take, yeah. Right. So no player has any incentive to improving his strategy, given that other players don't improve their strategies, they don't deviate from their strategy. Okay. So it's a set of actions, all actions that the ith player can take, right? So UI, I think, was called, okay, even here I should use, was called the payoff function. It's called payoff function. Yeah, it depends, right? Or utility function. I think utility function. Okay.
Total number of actions, not.
Yes, each player has m actions.
No. Then we would be considering only symmetric games. Nash equilibrium would be need not.
Yeah, so like whenever it exists or not exists. So maybe I'll put.
It's understood.
So maybe
All possible, but yeah.
all possible. Yes, so I'm not talking about symmetric games here. Okay, so does a pure Nash equilibrium always exist? So can you give me an example of a game where it exists? Okay. So I'm not drawing the table, but if you recall, the table was something like this. I mean, I don't know the entries of the table. Oh, okay. It should be, one was P1, the other was P2. Silent confess. Possible actions, right? So is there a game where Nash equilibrium does not exist, pure Nash equilibrium? Sorry, so many interfering answers.
Rock, paper, scissors.
Rock, paper, scissors. Yeah, so there are some more games. Okay, so I'm not going to write in the entries, but this again was a 3 cross 3 matrix. It was actually not a matrix, it was a bi matrix. So every cell had 2 entries. So we can think of it as 2 matrices, right? One for player 1, one for player 2. So I'll call this bi matrix. Yeah, you should think of it either as a bi matrix or 2 different matrices. So prisoner's dilemma is a yes instance. Is that okay? So what should be the next? Mixed Nash equilibrium. Okay, so I'll do that. Okay. Okay, so given a game G, so I'll write something. Let's see. How long is the board? Okay. So that question is okay? It's fine, is it? So let's say you design an algorithm for this, right, to find the mixed Nash equilibrium, and I mean to decide if G has a mixed Nash equilibrium, and I give you a game. So what will be possible answers?
It is finite players and finite strategies, it is true or false.
Okay. So maybe I should clarify that. Finitely. So number of players is finite, number of strategies are finite. Yeah, so maybe you should talk louder, or you should, all these look identical to me, so I can't figure out where to look.
As an essence to solve.
It's always a yes answer, right? So every finite game has a mixed Nash equilibrium. So decide doesn't make sense. Question is find a mixed Nash equilibrium. in G. So if it's a two-player game, right, you will have to actually come up with that strategy. Right? So right, such that that particular strategy is a mixed Nash equilibrium for the game G. So the existence is guaranteed. Right? Is that okay? You always know one exists. The question is you have to find it. Okay. So you saw something like this, Brewer's theorem. Can you describe the theorem, the statement, or whatever you recall?
The function is convex and continuous and discontinuous. So there exists a fixed point such that x equals to
Yeah, fixed point means fx equal to x. Right? Okay, so what are you given? You are given a, so I'll say continuous function on, I think, okay, so let me say continuous function f, give it a name. Or you can think of it as a continuous function from a disk to a disk. Okay. So it's like you have coffee and you are swirling the coffee with a stirrer, right? If the movement is continuous, you will find a fixed point. So find a point x such that, so this x is called a fixed point. So Brewer's theorem tells you that such a point always exists. The question is you have to find the point. Right?
Here only have issues with like real numbers.
Right, right. So it's not even clear. Like in your head, maybe you can find, but how is a computer even going to like input output these functions? I mean, how are you going to input this function to a computer itself is not clear actually. And the function is defined on 0, 1 to the n. So you can't tell the function what it is. Tell the computer what the function is. Right? You don't have enough time, space to actually represent this. Okay. So in fact, not just in this, in many of these problems there are going to be issues. Right? So you have to find out how a computer is going to solve this. So mathematically you can prove that there exists a fixed point. Right? How are you going to compute the fixed point? Yeah, so we'll come to all those representation issues. So here is another problem. Okay, so given a game G, oh, so did you see this by the way? I don't know if you have seen this already. Okay. So you are given a game G and a mixed Nash equilibrium. Let's say it's two players, so I'm just going to put, I want to decide if there exists another mixed Nash equilibrium. Right? I mean, there can be many mixed Nash equilibriums. Is there one different from this, or is this a unique mixed Nash equilibrium? Is that okay? Okay. So you saw parity games. I think Srivatsan introduced parity games. So can you describe what a parity game is? It's some game on a graph, but what is it?
In an infinite game, if the maximum number being repeated infinitely is an even number, then one player wins. If it's odd, then
Correct. So this is a two-player game. So maybe I will write it as. Just to recall what a parity game is. So there are two players, one is the even player, the other is the odd player, and you have an underlying graph. Okay, so I don't know if I have an example. Okay, I have. I don't know if I have space, but. Okay, there are some more edges, okay, and so on. Okay. So every vertex has a weight or a priority attached to it, and some more numbers. Okay. These priorities, let us say, are distinct numbers. Okay. So these are distinct natural numbers, and the token is placed on one of these vertices. Right. Whoever holds the token, he is going to make a move, and this graph is you ensure that this graph, every vertex has out degree 1. So this game can go on forever, right? Infinite sequence of moves can be made. Whoever holds the token is going to make the next move. Right? You get an infinite sequence of numbers, right? So that player wins. You look at which number appears infinitely often in that sequence. Whoever holds that number, that player wins. Right? So I don't know if you saw, but should there always be a winner? It's not clear. Right? Even that is not clear. If I give you a game, you are generating an infinite sequence of natural numbers. Right? Should one appear infinitely often? Right? So these things require a proof. But the question is, given a game. So a game is essentially, you are given a graph, the vertices of which are partitioned into even and odd, and every vertex is attached a number. That is the game. Right? And a start vertex V. Right. Okay, so maybe I should put more numbers so that it becomes. Some directions are incorrect. Decide if even has a winning strategy. So I think even, let us say, is circle. I don't know. Odd is rectangle or square, right. So if I start from 4, right, let us say 4 is the start vertex, right. So the token is placed here, he has to move, he will make a move to 1, right. Now from here, the odd player can either move to 4 or to 6, in any case 4 will win. In this infinite sequence, 4 will appear, 4 or 6 will appear infinitely often. So the largest number appearing will belong to even. Right? So depending on the start vertex, even may or may not have a winning strategy. So if the start vertex were 3, then odd will have a winning strategy. So you should check why odd has a winning strategy. But is it clear what a winning strategy is? So you play this game infinitely often, look at the infinite sequence of natural numbers, look at that number that appears infinitely often. If it belongs to even, even wins, otherwise odd wins. So if I give you this game G and vertex 4, then you should say yes. If I give you this game G and vertex 3, you should say no. Right? Odd wins. Okay. So is that okay? Like which one? I mean, these are things we have already seen. So. So if you look at prisoner's dilemma, rock, paper, scissors, these are non-cooperative games. So the players don't cooperate with each other, no coalition, right? So everybody wants to win. So that's one feature. The next thing is, it is a simultaneous move game. Players make moves simultaneously. Right. This is different from chess. So chess is a sequential move game. So first white moves, then black moves, then white moves. Right. So white can see what was the previous. Okay, if white starts, then black can see what is the previous move white made. Right. And if I play black, I actually have enough information of what possible moves white can make. I just don't know what move this player is going to play. Right. So Carlson knows what all moves Pragyananda can make. He don't know from that bag what he is going to choose. Right. Based on what he chooses, Magnus Carlsen should choose the next move. But here it is different. Okay. So these kinds of games, you know every information that is necessary to make the right decision. Right. So it's a game with perfect information. So this is different from cards. So cards, if 5 of us play cards, I don't know what card you have. I have imperfect information. So I cannot actually figure out what move you can make. Depending on the card you hold, there are many moves that you can make, and there are many cards that you may hold, I don't know, right? You are holding information which I do not know. So that is a game with imperfect information. I do not know information, right? So here I have every information. I can see all your payoffs, right? In chess, I can see all possible moves that you can make. It's just that from that bag, I don't know what move you are going to make, right? Okay. So this is a non-cooperative game where the agents don't cooperate. Now there can be games that are cooperative games, right? We all play, divide ourselves into teams. We want to maximize the payoff of the team, right? And then maybe let's say we win the game. Now there is a profit that we have achieved. How are we going to share it? This usually happens in the market also, right? Many employees are there, all of them work towards increasing the profit. Now the profit has come, how are you going to divide this profit? Right? So there should be a fair division. Whoever contributes more to the team should in some sense get more. So Shapley value makes sense in cooperative games. So the input is a cooperative game. So can you describe what a Shapley value is? So let's say there are n players. I think you've seen Shapley values yesterday or in one of the days. So what is a cooperative game? So maybe Shapley value is the next question.
Where valuation might differ if you correlate with some other group.
So there is some valuation that is given, right? Okay, so let's say take some example. There are 3 players. So all 3 of them are going to take a taxi. Okay, 1, 2, 3. So one independently can take 2. Okay. So if one takes the taxi, he has to pay 6. Okay, I don't know. 6. So I'll put some numbers which I have so that 12. Oh, I missed a subset. So if one takes the taxi, he has to pay 6 rupees. If 2 takes the taxi alone, he has to pay 12 rupees and so on. So the point is all the 3 of them are going to take the taxi. So in the end, when they get down, they have to pay 42 rupees to the taxi driver. The question is how are they going to split this 42 amongst themselves? Is that okay? So it's a fair division of expense. Like all the cities together coalesce and decide to build a road network. Who contributes how much for the road? So if we say this 42 rupees, you can divide it as 14, 14, 14. Is this fair division? So if one had taken the taxi alone, he would have paid only 6. So he'll be like, why should I join with you? Right? So it's not okay. So you can even say 0, I don't know, maybe 12, 30. Right? That is a solution. Yeah. So you are dividing 40 into different possibilities. Some of them may be fair for some players, it may not be fair for other players. He is riding free, so it's not exactly fair in that sense. Right? So it's not even clear what is the notion of fairness. That requires a proof. Right? So this is what Shapley did. So Lloyd Shapley was an economist. So these are questions that arise often in economics. So he came up with some notions of fairness. Correct? So maybe we should see. So I don't know if you have seen. So you should tell me whether you have seen. So in this game G, you have n players. Okay? And you have a valuation function, which is a function from 2 to the n to r. So some players can actually contribute negatively to the game. You have this player, your team is going down. Right? So it's a real number, it can be negative. You throw him out, actually things may get better. Correct? So there are situations like that in economics, in other places. Okay? So actually I don't know, have you seen this? Did you see this? Okay, you saw the formula was told to you. Okay. So maybe we'll see how someone actually came up with the formula, and then we'll. Okay. So I'm not going to do the whole thing. So the final thing is that what is going to actually happen in practice is the correlation. Like all of them are going to collude. Now the question is, after you collude, how you are going to split the profit, right? Okay. So the Shapley value of a player, I'm going to denote by. So I is the player number. If this was the notation, I don't know. Okay. I don't know if it is concordant with what was done earlier. So we are going to use this. So if I sum over the Shapley values of all the players, what should I get? The total, right? So you are using only 42, you should not like pay 50, right? On this set, right? Now if two players contribute equally, they should get equal payoff, right? So that is equal treatment of equals. Two people are equal, they should get equal money. Okay. So if I and J are two players, and for every subset S of 1 to n, if S union I is equal to the value of S union J, then the Shapley value of I should be equal to the Shapley value of J. In every subset they contribute the same, right? So you should not ask them to pay different amounts. If someone does not contribute to any set, he should not get anything. He has not contributed, right? So for any player I, if for all sets the valuation of S union I, right, whatever is the value, it's the same even without him, let's say, for every set, then the Shapley value of that player has to be 0. Say dummy player, and you can just throw him out and you'll still be fine. Okay. There are some other requirements like anonymity. If I flip the names, right, it shouldn't matter, right? It should not matter that he is this person. What is his contribution is all that we should see. So based on these notions of fairness, there is only one function that satisfies all these functions, and that is the Shapley value. So now I will write down the formula which you were asked to. Oh, okay. Times okay. So this is what he is adding to the set. After you add, this is the individual contribution player I is making. Before he was added to the set, this was the value. After he got added to the set, this is the value. So there is a meaning to how this came. We will see this in maybe in this next talk. But this is the formula for Shapley value which you have seen. Is this what you saw? So I don't know, did you see a notion of ordering? And so you also saw that ordering, right? So you look at all possible orders of these players, you see when you enter, they may have been some contributions. How much are you going to contribute? More when you enter the ordering. So that n factorial comes from the fact that you are considering all possible orderings. Okay. Yeah, so it requires some more proof, but I am not doing it. So if we have time, we'll. So maybe I'll erase this portion. Okay, so I'll just erase this portion to get some space, suppose. Oh, so by the way, I didn't complete that question. So you are given a game and you are given the valuation function, you have to compute the Shapley value of every player. Or maybe I can even say, and I compute the Shapley value of a particular player. Right, how much this person needs to get. So this is a game you all play, right? There are, let's say, two players, and there are a finite set of songs. You have to choose a song, the last letter of which should be the first letter of your song, and so on. Now you lose if you choose a song that has already been sung. That's the rule. Okay. So if you want to win the game, you have to ensure that this other person does not have enough choice, right? So whatever winning and all means, okay, so you know what Antakshari is, I am not going to explain what. Okay, so this is chess, but generalized chess, meaning that there is an n cross n chessboard. So you have to figure out how many pawns to keep, how many bishops, how many knights, it is not clear. In 8 you know there are 2 bishops, 2 rooks, 2 knights. So it is not clear, so rules of the game should be defined accordingly. The question is, given n cross n chessboard, white and black are playing, I will give you exactly how moves have to be made, how many kings, how many, I mean one king, let us say one king, one queen, but other battalion that you have you can change, there is a fixed battalion. So I will tell you whom to use, how to use. So you will say white has a winning strategy if there exists a move that white can make such that for every move that black can make, there exists a move that white can make such that for every move that black can make, and so on, and finally the game will end in a checkmate. Okay. So then you will say white wins, or maybe draw. Okay. So I have to define the rules accordingly, which I have not.
So what is the draw here?
Yeah, so I think, yeah, I don't know exactly. Sometimes they say if you make the same, if the board comes back to the same position several number of times.
There are 2 draws. If you do 3 times the same act, then it's a draw, and if you can't move, the other player can't move, there is no move available for him to do.
Can that ever happen?
Yes.
No move meaning you have run out of pieces.
Like say if you are the only king there.
Only king is there.
No, there can be other moves also, pieces also, but they can't move because they are blocked.
Oh, okay, that way.
So one, yeah. So there is a black piece that is trapped within a white, I don't know, all whites. You can't move, and or this the board comes back to the same position again and again. So that you should not do. I mean that's not legal, right? Then the game can go on forever. So and there are conditions for draw, which I'm not a chess player. So, but if you define that, then you can ask this question. That's what I'm saying.
In this, so do we see from black's point of view also?
Yes, so this question you can flip.
The white moves first.
Yeah, so does the black have a winning strategy? Yeah, all of these games are like, I can ask if does P2 have a winning strategy, P1 have a winning strategy. I just wrote P1, P2. Okay, so there are 14 games written, 14 problems written on the board. So the problems are written in increasing order of hardness. Okay. So primes is in the class P, generalized chess is EXP complete, for whatever all that means. So if you move on the board from left to right, the problems are written in increasing order of hardness, for whatever that means. I have not defined what hardness is. So if you ask the computer to solve primes, it will return immediately. If you ask it to solve chess, it may not return immediately. Okay. Yeah, so I have not told you. So things written in red, I will tell you. I have not told you what P also is. So the idea is, so I will retract the board. So at 12:45 I will bring this back. At that point you should tell me what the complexity of every game is. So after I introduce everything. So this one? This one is it? Okay. Okay. Yeah, so this will come back at the end after. Is that okay? Yeah, so if there are questions about the question, you should ask now. Oh, but there is something that you didn't ask me. Let's see. So there is a given in every problem. You never asked me how it is given. So how are you going to give things to a computer? How will you input a number to a computer? Binary. So n is given in binary, right? That's okay. So how do you give a formula to the computer?
You can decide an encoding.
Hmm?
You can decide an encoding for each variable.
For each variable, okay, and then?
You can decide encoding for each connectives encoding.
And then what do you do?
And what do you mean?
So now, if I give you the entire truth table, right, and ask you, is there a 1? You will just scan through the truth table and see there is a 1. So that is a satisfying assignment, that corresponding row, right. So if I give you the truth table, it is easy. So now what you are saying is you are going to fix an encoding for every variable, right. So I suppose what he means is, yeah, actually it's exactly what he means. So this I am going to give as a graph, right, and maybe I will do some traversal and then input it. So the point is I should not give the formula as a truth table. Well, I can, but then even to read the input it's going to take like time 2 to the n, where n is the number of variables. Then the problem is easy in the sense I will scan through the table and tell you whether it is satisfiable or not. Is that okay? Right? There is a 1, then it is satisfiable. So if I give the truth table, then all these problems are actually like easy. You can find the satisfying assignment, go to the row and output the row, right. See the number of ones, that is the number of satisfying assignments. Right? But the point is that for the computer to even read the input, it is going to take a lot of time. So time as big as the truth table. So what is the size of a truth table of a function on n variables? This is JEE question.
2
2 to the n. 2 to the n possible things, and then there are outputs also. So you have to represent 2 to the n plus n times 2 to the n plus 2 to the n. All the inputs, all the outputs. You give the computer everything, it is going to tell you what it is. Just that the computer has to read all this information, for which itself it will take a lot of time. Right? Okay. So even here it is not clear how it is given. So maybe you will input the matrix, the by matrix. So how much size will it require? So there are n players, m actions. So here there are 2 players, 2 actions, it has size 4. So you should.
M power n.
Okay, not clear. Actually, I can neither see nor hear, that's all. So you should.
M power n.
M power n. So m actions for each player, I suppose. And there are n players. So roughly like. It's going to take a lot of time to even read the input. Well, if he reads the input, he can actually find the equilibrium. Can scan through the table and look at every possible strategy. This requires something, this requires that the utility function is efficiently computable for whatever that means. Now it should define. So the point is that how you represent the input to the computer is important. Depending on that, you have to define the notion of time. Okay, so that's what I am going to do now.
For evaluating that file in this.
Exactly, this one, right, should be efficient, or whatever efficient means, I am not defining. Okay, so we will start with the first problem. This you should do. So can you give an algorithm to solve primes? No, you don't know of those 3 people. You are not one of those 3 and you don't know those 3 people. So this you should do.
We call the primes till root of that number and try dividing it.
That's okay, like agree. And if there is a factor, it's going to appear from 1 to root n. So what is the running time? So let's say division is free. I mean, how long does the loop run if you write an code for this? Root n. So I'll put odd, some division and all you're doing, which I said is free. It's not really free. So how long does this algorithm take? root n time. How is the input given? Log n bits, right? So this algorithm is that okay? So it's something like 2 to the log n, roughly. And exponential is not good in practice. So if you look at the way e power x grows, right, even with small changes in x, e power x is going to grow much faster than x, right. So as the input increases, the running time becomes drastically large in the input, right. So this algorithm is not efficient. Okay, so now the question is, what is efficient, right? Input size. So the input is log n bits, right? Yeah, so we write this for input, some shorthand. Okay. So now the question is, what is efficient? So many people did think about it, what is the right notion of efficiency, and the agreed upon practice is, so for all these problems, let us call the input, now I think it is okay, right. X is the input, it is in binary, right. So you say an algorithm is efficient if running time is polynomial in length. So there are reasons why we say polynomial is the right notion of efficiency. So this is like time okay. So this was first put across by Cobham. That polynomial time is the right notion of efficiency, right. So they were actually working on implementation problems, and they realized that some of the algorithms that run good in practice had running times this, where n is the size of the input. So n essentially is the length of x. Okay. So these are polynomials are moderately growing functions. They don't grow as much as e power x. Yeah, so it can be something that is positive. Well, there is some issue there. So if you say n to the 0.5, so his question is, can it run in n to the 0.5? So then you have not seen all the input. So I don't know, like without reading the input, how you are going to give an output. 1.5, yeah. So they can be real numbers. Is that what you are asking? Like positive real numbers, yeah. So n to the 1.5, n to the 2.5, but the question is, can it be n to the 0.5? So people also study such algorithms. Sublinear algorithm. So have you seen a sublinear algorithm?
PCP has some sublinear algorithms.
What has?
PCP.
What is PCP? Probabilistic checkable proofs, you mean? No, something. Binary search. Runs in time log n, input has n. It's an array of size. Yeah, PCP has many stellar things which we don't like completely understand. So is this okay? So these are moderately growing functions, polynomials, and they are composable under addition and multiplication. So if you combine, if you have two algorithms that run in polynomial time, you can like run one after the other, the algorithm is still polynomial time. That's the point, right? So you can divide this and give it to different people, and they can all come together and paste their algorithms. Will still run in polynomial time as long as the number of modules is polynomial. Okay, so So there is something about problems 1 to 4 and some of these where the answer is yes, no, right. So such problems are called decision problems.
So in the above example are, so inputs were log n, right? Log n bit. So the mod x was log n bit.
Correct. So a good algorithm for prime should run in polylog n time, whereas your algorithm runs in 2 to the log n. So it's not a good algorithm. Well, so people have come up with a good algorithm. Oh, okay. Okay, I will fill it up. Yeah. Yeah, so they gave an efficient algorithm for primes. Okay. So decision problems 1 to 4 are decision problems. So you have to decide yes or no. So you say a decision problem B So, P is a class of decision problems. You put a decision problem inside P. If there exists an efficient algorithm, so the algorithm has to have running time polynomial in the input size, right, that correctly decides all inputs to B. So, if I give you an yes instance, this algorithm has to say yes. If I give you a no instance, it has to say no, right. So, for every input that I give, my algorithm should decide correctly, right. So, it should decide, give me the right answer on all inputs, right, and it should run in polynomial time. Is that okay?
So some random algorithms sometimes give incorrect answers. So will they come under polynomial time?
No. So this is only deterministic. So it should always give the correct answer on all inputs. So that's a different class, RP. So now I can. So Agarwal, Kyle and Saxena, AKS primality test is a polynomial time deterministic algorithm to test if a given number is prime or not. Okay, they won several awards for this. I mean, it's not as easy as this. It has won many awards, so it should not be, right. Okay. So there are a bunch of many problems. So maybe I should retract. So is there a way in which you can
Pull that down, one at the bottom. Here.
So can you do this? Can you come up with an algorithm to solve this problem, odd cycle detection? So someone asked me what exponential time is, right? So which means that the running time is 2 to the x, right. So that means it's in exp. Now you come up with an exponential time algorithm, which you did, will put primes in exp. The question is, can you get a better algorithm for primes? If you get a better algorithm for primes, an efficient one, it will move from exp to p, right. Yeah, so this one you should try. So you want to check if there is a cycle of length 3, 5, 7, 9 and so on. The largest cycle that can be in the graph is n. N is the number of vertices. Take all possible subsets of odd size, check if that forms a cycle. So what's the running time? So order 2 to the power n, so it's an exponential time algorithm. So now it's an exp. Can you bring it to p? Okay. Just thinking of coloring.
We'll take only odd subsets.
But that's all subsets are still like n choose n by 2. Yeah, so if you have seen graph traversal algorithms, right? What were you going to say?
Well, I was thinking of coloring because
Coloring, okay, so what do you want to color?
its neighbors should be of a different color.
So you're coloring vertices or edges?
Vertices.
Vertices, okay. So I will use, I don't know, red and blue. Okay.
Color its neighbors.
So give one color to the first vertex, one of the vertices, give its colors a different color, give its neighbors a different color. Then, and then you continue doing this.
Yeah, but that would not do.
Okay.
Yeah, but again for 4C its neighbor is the same color. So
if you get that, then it's an odd.
Okay, so this is an exercise. So you do this coloring. At some point, if you find an edge where, I mean, at the end of the coloring process, if you find an edge where both the vertices have same color, it has no offset. This requires a proof which you have to do. Okay? So this will require you to color the vertices and simultaneously traverse the edges. So you have to traverse all the edges in the graph, right? So the running time is something like order E. I mean, some more things are there, maybe V plus E or something, right? You have to color also, but which is part of the input. The graph you have to represent, so you will represent this graph as an adjacency matrix, maybe, or as an adjacency list. So every time you have to move to the adjacency matrix and check whether there is an edge. Okay. So this is in P via the algorithm that you gave me, right? It requires a proof that this coloring actually finds an outside color. Is that okay? So this one, next. So I'll call it SAT. So can you come up with an algorithm? So is it okay, like so far what's going on? Like there are some problems, there are some algorithms, there are some complexity classes. So it's 11:15, right? So the input is given as a graph, right? A graphical way to represent this Boolean formula. So the variables, the leaves are all x1, x2, xn, and the gates are all internal vertices are and or not, and so on. So there is one property about SAT. So SAT is an exp. You can just substitute all possible Boolean values to the n variables, and then you have to traverse the graph bottom up and evaluate. Yeah, evaluation and all is easy. Correct, correct. So define exp to be?
No, you didn't define EXP.
No, I said what exp is, it's written.
Oh.
Yeah, I said. Okay. An algorithm is in exp if it runs in time 2 to the x for all inputs. So you substitute, you traverse a tree bottom up, evaluate the tree and see what is the value at the root. If it is 1, it is a satisfying assignment, 0 otherwise. There are 2 to the n possible assignments, try all of them. Record them in a table. When you find 1, you will stop. Is that okay? So SAT is in exp. So you started with primes in exp, then we saw someone showed primes is in P. Then OCD you gave an algorithm that runs in exp, like look at all possible cycles. Then we found a polynomial time algorithm. So what should you ask? Is SAT in P? Okay. So it's a very relatively hard question. I'm going to define what hardness is. So you should not try to find a polynomial time algorithm in this talk. So it's possibly not possible. So you should focus on what is going on. So don't try for a polynomial time algorithm. So what property does SAT have? Right? Suppose it's a yes instance, right? Then what do you know? There exists an assignment that satisfies this function, right? So, is this clear? Right, it is indeed satisfiable. So, suppose I flash a formula on the board, which is that one, and then you say, I know it is satisfiable. So, I will ask you how. So, what will you say? You will give the assignment. Right? What will I do? I will verify the assignment. If it is 1, I will tell you, yes, you are correct. Suppose I gave you x1 and not of x1, okay, and you came to me saying, hey, this formula is satisfiable. What will I ask you? Give me the assignment. What will you do?
Give some assignment.
You will give some assignment, some bogus assignment. What should I do? Is not possible, right? Is that okay? So, it is a property of the problem, right. So, SAT is so what do I mean by that? There exists a verification algorithm let us call the algorithm V, okay, that on input, okay, I should say such that. So, yeah, so maybe I will define it correctly so that I can use it. Okay. Okay, so I will define it slightly more general than SAT so that I do not have to spend more time. So, you say a decision problem B okay, so maybe I should say such that. This is the maximum, right? Oh, okay. Instance, should give a name. Yeah, I will describe what I am going to say. So, you will say a problem is efficiently verifiable if there is a verification algorithm. The algorithm that I did, you gave me an assignment and I evaluated the graph on that assignment, right. So, the running time of the algorithm which I did is polynomial in the graph, I mean it is just bottom up evaluation.
Efficient verifiable means polynomial.
Yes, so efficient everywhere means polynomial. From now and for the rest of your life, efficient should mean polynomial time, okay. So, anything other than that is inefficient. Okay. So, if there exists a verification algorithm such that for every input instance, so for every phi, right, phi may either be a yes instance or a no instance. So, for example, if it is x1 and x2, that is a yes instance, if it is x1 and not of x1, it is a no instance. If it is a yes instance, then there is a short proof which is just a1 to an. When I mean short, the number of bits that you are giving me as a proof is polynomial in the input size, and the input already has all the variables, right. Short proof such that I can take this verification algorithm, take the formula phi and the assignment A and immediately accept, right. And if it is a no instance, then no matter what assignment you give me, I am going to always say no. Is that okay? Yeah, so if there are questions, you should probably ask.
Inefficient verifiable. How will you
So you want to define what?
like if you give me some assignment, I can polynomial, and I can say that it is just right.
Correct.
So what are instances that I can't say in polynomial?
So you want to say that
Verification is not polynomial.
Halting problem.
It can't.
yeah, we cannot decide,
Yeah.
which is correct. You can't verify if the machine halts or not in.
Let's say these are
But you can't decide at all in it.
That's
So this should be easy. I want to say that.
so any XP question, like in hypothetical speaking, any XP, non-deterministic.
Yeah, so there is this class called NEXT, so I don't know how to say that.
But there are.
But there are.
So that class is NEXT. So I have not even defined N, the word N. So maybe I should define it and then I'll tell
Did
you.
you try to say that almost all would be efficiently verifiable? It feels almost like most of the problems.
Yeah, so
Even-
most of the problems. So there are things beyond NEXT also. See, suppose I give you a formula and you are coming to me saying that I know that this formula is satisfiable. So I tell you, give me the proof, and you are saying no, it will take me like 6 years to tell the proof. I am not going to wait here and listen to your proof for 6 years, right? So the proof should be short. So you are saying the algorithm is efficient, meaning it is going to invest only polynomial in x, time in all. So it should not take it eternity to read the proof, right? So short means poly. So here it is A1 to AN, right, which is just n bits, which is short compared to the size of the formula, which is the input. So now you can say those problems are efficiently verifiable if the yes instances have short proofs that are efficiently verifiable. If it's a yes instance, there is a prover who can come to you and say that here is the short proof, and there is a verifier who can efficiently verify by reading the whole proof. Now what he said was something slightly different. So there are cases where the proof is very large. So the verifier does not have enough time to read the proof, right? So he will look at certain bits in the proof and then he has to decide whether the proof is correct or not. So what bits he has to read? He will use some randomness.
In this, we are
But that's not what we are going to do here.
given proofs or instances.
So you say SAT is efficiently verifiable. Right? SAT is a decision problem. When do you say SAT is efficiently verifiable? If you can write down a verification algorithm. So you should describe the algorithm. What is the verification algorithm going to take as input? It's going to take as input the formula phi, which is the input, and the proof. Right? So if it's a yes instance, then it can say yes.
Proof meaning our algorithm that we wrote for verification.
No. So proof is the assignment. So SAT is a decision problem.
Whatever assignment is given, that is
Yeah. So SAT is the decision problem. So what is the input instance? It's a formula phi. It could be anything like x1 and x2 or x1 and x2. So this is given as a graph.
that is the
That is what an instance is, right? So now what is a proof or U? That's your assignment A1 to AN. Right? So you say SAT is efficiently verifiable because we came up with a verification algorithm. The algorithm that takes the graph corresponding to this, takes the assignment, plugs in the assignment at the leaves and bottom up evaluates. So that's a polynomial time algorithm. Right? So you have to describe the verification algorithm, and this algorithm has these two properties. If it is a yes instance, then it will accept the short proof. If it is a no instance, no matter what bogus assignment you give, it will reject. Is that okay? Yeah, it may take some time to digest, so you should digest across the break. Okay, so NP So, everything that is efficiently decidable is also efficiently verifiable. So, that is something you have to check. I will give it to you. Okay. So, okay, so we do not know if these two classes are same. So, our problems in NP also in P. Right. So, I have to describe something else. So, maybe we will do after the break. Right. Okay. So, if you are taking notes, please take the open, right, so that you do not go out and proclaim.
Showing this would be catastrophic.
What was the question?
Because this is open. Suppose you close it.
Yeah, I think we will get $1 million.
Yes, claim millionaire.
It has happened
Claims
before, right?
They would-
It is the open.
But the loss would be
Yeah, there will
So I did not get-
and you winning $1 million. Like it would be a much more significant.
So, what did you say? I did not get.
I mean, if you erase the open part and leave it as it is, maybe somebody comes in the next lecture.
Now you have proved it.
That's exactly what I don't want you to go out and proclaim that I have proved it. I don't have problems with others doing it. I am not going to try my hands at this. That's all. Okay. So, we will come back and try to solve. I don't know if I will be able to cover all of this, maybe some of this.